Hi everyone, and welcome back to Fundamentals of Engineering with Mechanics of Materials, Maximum Deflection Calculation in beam. In this example, we have like a cantilever beam of AB, this time handling a distributed load of W. We want to calculate the delta at B and also theta at B. Solution 1, our solution is integration method, and we are integrating the elastic curve of the beam. So first of all, if we just convert this distributed load to a concentrated load which applies at the center of the beam, and that's equal to the reaction R sub A, and that's WL. And definitely in the fixed support, this distributed load creates a moment, and that's MA, that's equal to WL squared over 2. These are the reactions at the fixed end A. And if we cut our beam through by delta by a length of x and develop the moment equation there, so definitely the convert the distributed load to a concentrated load of Wx, and that's applied from x at the center, or x over 2. And if we just jot down the moment equation, summation of moment in x goes 0 is equal to, it just gives us mx, counterclockwise direction is positive, plus WLX times x over 2, that makes it like WX squared over 2, plus WL2 over 2 minus WLX, that's equal to 0. And those are nothing but this is like RA, which is WL, times the length x makes a moment. And then this one is just the concentrated moment in counterclockwise direction, and that's like MAW L squared over 2. These are just the reactions of fixed end due to this loading. And then it just says mx is equal to negative Wx squared over 2, negative WL2 over 2, plus WLX, that's our moment function. And if we just integrate our moment function once, it gives us the theta at B, and by integrating theta, it just gives us the maximum deflection function, or deflection function, and you can calculate it for any point at the beam because this is just the function. By each integration, a constant comes to our equation C1 and C2. So by two consecutive integration from m sub x, you will reach to delta function. And by applying the boundary condition, we do know at x is equal to 0 at the very beginning, there is no theta, it's fixed. There is no delta, there is no downward or upward movement because of fixed support. So they give us the constant C1 equal to 0 for theta, and then delta is equal to 0. It just gives us C2 equal to 0. As soon as we know what are our constant, we can get the real delta function for the entire beam, which is this function. And now by applying the boundary condition at the free end, x equal to L, theta is equal to this amount we calculated. So we have like our theta function. This is our theta function. Use L instead of x in the function. You will reach to this term, and by simplifying the equation, it just gives us theta is equal to negative WL cubed over 6EI, which you can see it here. Likewise, if we apply the other boundary condition at x is equal to 0, theta is equal to this one, And also, if we calculate delta, let's replace all the x in the y function by the length of L, because that's at x equal to L. If you do so, it just gives you replace all the x by L at the free end, and it just gives us a delta is equal to a negative WLQ L to the force over 8 EI. So by the integration method, we just calculate the theta and delta function for a cantilever load, a cantilever beam of AB handling a distributed load of W is a WL cubed over 6 EI for delta, and WL to the force over 8 EI for delta. Thank you. We'll solve this problem with the solution 2, which is moment area method, in next video.